Hello and welcome back to another episode of the Web3 Insights podcast series. I'm your host, Aaron Hayhurst, and today we're diving into a topic that's generating a lot of buzz in the tech world, the intersection of quantum computing and Web3 cryptography. Joining us today is Ian Smith, who is the CEO of QEVM, a leader in quantum computing technologies. We're going to be discussing the potential risks, challenges, and opportunities that quantum computing presents in the world of Web3, and particularly in relation to cryptography and security. So, Ian, it's a pleasure to have you on.
Thank you very much. It's good to be here.
No, fantastic. For me to give a bit of an introduction for those that don't know, QEVM or quantum EVM is basically at the forefront of blockchain innovation, introducing the world's first quantum resistant EVM designed to future-proof blockchain technology. Quantum EVM basically integrates cutting-edge quantum-safe cryptographic protocols to protect against the impending threat of quantum computing. So, moving on into the podcast, Ian, the first question. So, quantum computing has the potential to revolutionize many industries, but it also possesses significant risk to current cryptographic methods used in Web3. How imminent do you think these threats are, and what are the most sort of pressing challenges that Web3 developers should be preparing for?
So the Eli 5 that I like to give, the short explanation is that we used to have these algorithms that says we need 100 million qubits. We need, a billion or 2 billion or 5 billion qubits. And it had to be in this one gigantic machine that we just can't build. And the projection on when we would be able to build that was 2030, 2032, somewhere around in there. And last year, the algorithms changed. They improved far better than expected. We had this expected, increase in the hardware. We had an expected, decrease in the hardware requirements from algorithms getting better and better over time. But last year, the requirements dropped significantly because now we can use machines that we can currently build and use them to break elliptical curve cryptography at 256 bits and RSA at 2048 bits. It used to be we had to have it all in one machine. Now we can take hardware that's currently in mass production and we can use it to, after we have enough of them, attack cryptography at that point. And that's projected to be 2026 or 2027 by a multitude of companies. So the main reason that the risk is so dangerous for blockchain and not other industries is that everybody else is able to switch their cryptography. They can they just upgrade SSL. Signal has already gone post-quantum. Apple has gone post-quantum. Google has gone post-quantum. Your latest Chrome browsers are already quantum safe. The
Nice.
problem here is that they're able to exchange their public and private keys and upgrade them as necessary. When you look at blockchain, the private key is your ability to spend money, and then the hash of your public key is how that money is delivered to you. So when you send someone money, you're sending them a message to a hash of their public address and public key. Now, a quantum computer can take that public key and convert it back into the private key through something called Shor's algorithm, which you can read a lot about. And there's actually some great YouTube where Peter Shor explains his algorithm in 20 minutes plus 5 to 7 videos for just the precursor to have enough information to understand what he's saying. But
Nice.
this algorithm uses discrete logs, and that's taking and finding the base given an exponent, and the result. So this will break pretty much every piece of cryptography out there, from elliptic curves to RSA, Diffie-Hellman. It'll break some of the old PGP cryptography like El-Gamal. They all rely on discrete logs as the hardness of the security. Now, RSA can also be factored, and Shores also specializes in factoring. So you might see things about that as well. Now, when you look at the cryptography involved, we can swap out the hash, and that changes the address that the money is sent to, but you still have the same private key. It's still considered your money. And you'll see an example of that looking at Bitcoin Cash. They changed the hash algorithm for Bitcoin, and they copied the ledger. And by copying the ledger, everyone still had a balance now in Bitcoin Cash. And then they changed the address. So it's a new address, and that was a safe operation. Everyone still had this cryptography that had been sent to them, the cryptocurrency. But when you change the public-private key system, everybody's balance is now zero. You've lost the ability to prove that the funds are yours. So there's a series of mitigations and migrations. Now, the main mitigation is to have like this long process where people can sign from one signature scheme to a new signature scheme, and they have to sign using the old address, and then they get the money on the new address. That migration has occurred already for Bitcoin back about a decade ago. And something like 15-20% of the BTC is actually under the old scheme. And the old scheme had an exposed public address. So those 15-20% of Bitcoin can actually be attacked with a slow quantum computer. And they can take the money out of those wallets and then spend it, basically selling Satoshi's coins. They would be able to essentially crash the economy to Bitcoin, even if it took a week or a month to solve those addresses or those public keys. Now,
Sure.
the critical issue here is that with the new algorithm, they can just keep making more of the same machines and increase the speed. So if it takes a week to solve the first, couple of Satoshi's addresses, then after that, they can just keep making more of the same machine, and then the time goes down from weeks or days down to hours and then minutes. And the algorithm created by Litinsky details the exact hardware specifications to crack Bitcoin in 10 minutes. That's what he's targeting. And he does this not just for one quantum computer, but 3 different architectures: photonics, trapped ion, and superconducting. Now, those basically 3 hardware manufacturers are leaders in those respective technologies. PsiQuantum is making mass production photonics, and it's a modular system. It's horizontally scalable. Just like adding more web servers, they can just add more qubit machines, plug them in, turn them on, and the whole thing gets faster. And we didn't think that it was possible to break the problem space up. And instead of breaking the problem up, they broke messages, and they spread them out into these logical qubits. So the new architecture is requiring 1152 qubits, which is what IBM made with their superconducting architecture back in 2023. And they need 6,000 of those machines. At that point, they're able to solve Bitcoin within a block. They're able to look at the mempool, see a transaction that has occurred, it's submitted by somebody else, solve that public key that had just been revealed for the very first time in that transaction, convert it into the private key, submit a new transaction, pay more of a mining fee, and then front run the legitimate transaction with the attacked one. And so that compromises the entire network. And 10 minutes is gracious. It assumes that there's no congestion on the network. One of the things that this is really dangerous for is smart contracts, because if you're interacting with a smart contract, you're exposing your public key, and that's usually a permanent ledger. There's a few innovative chains that make it a temporary, where you have a new address each time, or rotating schemes. And these are mitigation techniques because they still use elliptic curves. They still have the same weaknesses. They're just trying to shore up the defenses and make it a harder target. Monero and Zcash are vulnerable. People will be able to look at the entire history of transactions. The problem here is that the privacy would be revealed probably before the statute of limitations has expired for some people.
Right.
So it's going to affect a lot of things, and they can just take the money out of the transaction. Another
For sure.
issue for
In
smart contracts is the ability to substitute libraries. So even if there's a partial migration, some administrator can have a smart contract. You interact with your quantum safe wallet, and you interact with the contract, and it just takes your money through an exploit. So,
Okay. Sound. So, I mean, while quantum computing obviously prevents these types of risks, I also understand that it offers unique opportunities. How do you see quantum technologies being integrated into the Web3 space to enhance security and create new possibilities? And are there any specific developments, particularly at QEVM, that are particularly exciting in this regard?
So there's long term, and then there's medium term, and there's short term. And I'll
Okay,
answer because you asked starting off with the longest term.
sure.
There's actually the ability to do cryptography with quantum networks. And this is a little bit beyond us, but we've seen the mathematical structures on how to do this. There are some quantum networks that already exist. There's a banking network that it's basically a hardwired network. And it's immune to eavesdropping, and quantum physics guarantees that it's immune to eavesdropping. It breaks there's this issue in quantum mechanics where you can't know both the position and the direction
Right.
of a photon, and that's a similar problem. They've validated this over and over. You can't know both things at the same time. And that quantum network is secure because if anyone eavesdropped, it would reveal based on the fact that the message wouldn't arrive correctly. It would be gibberish. South Korea Telecom has already made a quantum key distribution network, and they have a quantum network as well.
Okay.
And so that includes the cryptography that's specifically for quantum computers only. There is a bunch of advantages. One of them is there was a paper from a few years ago that talked about how an experiment was done using quantum computers from two different manufacturers, where they basically emulated a wormhole minus the gravity. So some scientists say, well, that wasn't really a wormhole, but it uses properties of the holographic universe. And they were able to transmit a message from one quantum computer to a different manufacturer, different hardware, different scheme, same equation. So they were able to actually send a message from one to the other without, without connecting them. So this was disconnected networking. This was a wormhole of
Yep.
information. This was a way to transmit information in violation of the speed of light, the constant for the universe that determines almost everything, including properties of space-time. But they were able to skip that and just send the message directly from one quantum computer to another, point-to-point space, or point-to-point between two locations as if it were a single point. So that is a massive shift. One of the people that I talk with frequently is working on a new kind of blockchain that probably won't exist for another 10 to 20 years. But the idea is that you'd have a
Interesting.
device in your pocket that would be your wallet. It would be a member of a quantum network. It wouldn't plug into anything except maybe you'd charge it once every couple transactions or every couple hundred transactions. But this
Nice.
quantum device would be able to exchange onto a ledger that is the quantum network. The midterm, one of the things I see happening very soon is it will need bridging between classical systems and quantum systems. And the quantum computing has these advantages where the more and more information is in one location, the more efficient it is, which is the inverse of the way it works in classical computers. You want to spread it out as much as possible in classic computing, and the algorithms are designed to basically break up the information as much as you can. In quantum computers, you can actually query multiple times for around the same cost. So if it takes you, 5 seconds to do one query, it might take you 6 seconds to do 100. Whereas it's actually, in classical computing, it would take you 500 seconds plus some overhead, the scheduler, as well as the sorter and the distributor. So it's actually much faster to do it on quantum computers. To take advantage of that better, we need to have a bridge between quantum computing and classical computing. And one of the great ways of distributing trust is, blockchains. So you don't need to
Sure.
necessarily trust every member, you can just trust the cryptography. Unfortunately, that trust is going to be violated for classic blockchains. And that brings us to the near-term possibilities. When people realize that the money can be taken out of their wallet, it doesn't make sense to call it like forever money anymore.
Sure.
When there's no longer any privacy associated with the transactions you did 3 years ago, why do new private transactions? Zero knowledge systems will be broken, so if you put your ID on chain, and someone can just retrieve your private or your secret information that was stored inside that zero knowledge system. Now, there are some zero knowledge systems that something called Starks, which uses SHA hashes, which will still be secure probably for at least 5 years, but maybe for the next 100. Those SHA-256 hashes are used to uniquely identify information. And so they wouldn't be able to forge a new passport in place, but they could create a new ZK and they could unravel the ZK that's been performed if it's a snark. If it's a Stark, then that would be still private. Now, one challenge here is that a lot of people are just jumping on the classical efficiency, and StarkNet is not quantum safe. They have 3 unsafe technologies also named Starks, and they have one thing that is quantum safe called a ZK Stark. The other thing that we're going to have is fully homomorphic encryption. This is like a spreadsheet where you get to, like, say, add 1 to every number or divide every number by 2, but without actually knowing what those numbers are. And so the information is private even to the person doing the computing. Like, you get to run a formula against every cell of a spreadsheet without knowing the contents of the spreadsheet. And it's both provable, private, and verifiable. So that's another, near-term advantage. It's been done for, there's a couple different, like Zama is a project that's running on Ethereum, but because it uses not safe cryptography, because it can be broken by quantum computers, they have to re-engineer some of their tech. And so what we're going to need is entirely new infrastructure. And that's not
Right.
just the ZK and the FHE. That's going to include the exchanges. It's going to include the brokers. That's going to include the fiat on-ramp and off-ramp. It's going to be a completely new ecosystem. And so we're trying to make a clean ecosystem that doesn't have any unsafe cryptography inside of it. And then people can deploy backup copies of their infrastructure that's now compiled for our network. just by hitting compile is what we're aiming for. And then that quantum safe version is going to continue running. And then when the users realize that there's a problem, they'll be able to migrate. And they'll migrate to probably whoever has the contracts deployed. So it's unlikely that someone is going to be able to replace Aave or Uniswap on the classical blockchain. There's just too much market share. It's even if
Yeah.
someone spent 100 million on marketing, they probably would only make a small dent and attract a small number of new users. On the other
Hmm.
hand,
Hmm.
as everyone migrates from the unsafe classical blockchain and goes to the quantum safe, that's a new number one. There's a possibility that there's a completely different group that's operating those technologies, operating a DEX and offering all sorts of privacy preserving tech on that new chain.
Nice. So, in terms of like, off the back of what you sort of said there, and the opportunities that this has, from a short, medium, and long-term perspective, and someone at the forefront of quantum computing, what advice would you then give to Web3 projects and companies regarding future-proofing their cryptographic systems?
That's a bit of a hard question. You can do things at the wallet. There's these things called Lamport signatures. They're 307 times larger than a normal transaction.
Yeah.
But those Lamport signatures are just protecting the wallet and not protecting the chain as a whole. So there's a lot of issues with exposing that information. If you're currently building on Web3, I would recommend trying to find infrastructure. I haven't found any that is quantum safe. So we're making a layer one blockchain to have that first piece. And then it's possible to build fully homomorphic encryption, and ZK starts on top of that infrastructure. If someone is building infrastructure, I'd love to hear from you. Join our Telegram, say hi. Because we need to build an entirely new set of infrastructure.
For sure.
And one of the other challenges is that in classical computing, we use a lot of things to get multiple signatures. Multi-party computation is an entire field. And the techniques that exist in multi-party computation do not exist in post-quantum systems. FHE does, but not BLS. And BLS is what people use for rollups. It's what Solana uses for verifying. It's something that's being proposed to be used in Ethereum. Lightning Network uses BLS in order to aggregate all the signatures together. Basically, instead of checking all of the proofs one at a time, all of the signatures one at a time to make sure that every validator is correct, they can just kind of multiply them together, merge them into one signature, verify the one signature, and if it checks out, they know that everybody was telling the truth. So if anybody lied, then the resulting end signature that's checked is not going to be valid. That's
Right.
it's a great cryptographic technique. Unfortunately, we have to throw it away. And so now we're going to need to do sharding. We're going to need to spread out transactions. We're going to have to reduce scope. DAGs will be useful, but only if they're doing closure, which IOTA, they talked about having a DAGs, but they actually did cycles. It needs to be acyclic and flow in one direction. And it needs to also be this idea of no transactions left behind. That's the idea of closure. So every transaction that's submitted needs to be included. You can't just leave them dangling indefinitely and still have safety. So a lot of the horizontally scaling DAGs don't have closure. So if you see DAGs and they don't have closure, talk to an expert who understands this very clearly. But in terms of creating like sharded networks, we're building on top of a layer zero. We'll have network compatibility with everybody else that's using the same layer zero cell frame. So it's possible to have, a version for Cosmos and Solana, be able to have multiple migrations occur at the same time, and then build one unifying ecosystem. And then when Satoshi's coins get moved, we need to burn all the bridges. All of the classical, blockchain needs to basically be discarded. Um, and the best way to do that is to simply turn off the bridges that connect between the classical and the quantum safe blockchains. And then we'll be in a bridgeless economy where we'll be able to just transmit directly and send from a smart contract in the Solidity, Ethereum virtual machine into maybe a Solana virtual machine inside the contract, and just have the go down to the base layer, up through networking, and then up to the Solana virtual machine, or a style of it. There's a lot of variety that's possible, and I think that horizontal scalability will need to revert back to sharding, essentially.
Cool, cool. And you mentioned before we jumped on the call there, you're doing a talk next week, is it? Where is that? Did you want to maybe highlight that?
I'll be at Istanbul Blockchain Week. I'll have a 20-minute presentation. I'm not sure which day yet. And I'll basically be explaining these things on stage. And hopefully I'll have time for a question or two. And I'll be talking about this interview in order to help, provide a little bit more context, or a second version of the same thing. And
Nice. Okay,
then
great. Well,
I'll be going
yeah, go
around
on, sorry.
talking to lots of people.
Cool. That's good. That's good. We'll watch this space to anyone sort of following the podcast. Look out for these talks from Ian. I mean, thank you so much, Ian, for sharing your insights. It's a fascinating topic, and thanks for sharing it on the sort of fascinating intersection between quantum computing and Web3. It's clear that while there are challenges ahead, there's also significant opportunities for innovation and collaboration between these sort of two cutting edge fields. For our listeners, stay tuned for more episodes of Web3 Insights, where we'll continue to explore the future of decentralized technologies with industry leaders. If you enjoyed the episode, don't forget to subscribe and share with your network. But yeah, Ian, thank you very much. It's been a pleasure to have you on today.
Thank you very much. I appreciate it a lot.